The solar system has captivated human curiosity for millennia, and even with the advancements in technology and the wealth of knowledge accumulated, it remains one of the most profound mysteries of space. Understanding the solar system requires delving into its origins, structure, the various celestial bodies it hosts, and the interactions between these bodies. Every aspect of the solar system, from its birth to the mysterious forces at play, opens a doorway to even more questions about the universe and humanity's place within it. Before we continue, subscribe to the channel so you don't miss out on any of these videos. At the heart of the solar system is the Sun, a massive star that powers all life on Earth and drives the dynamics of the entire solar system. The Sun, composed primarily of hydrogen and helium, is a gigantic fusion reactor that converts hydrogen into helium, releasing vast amounts of energy in the form of light and heat. This fusion process occurs in its core, where temperatures reach millions of degrees. Over the course of its life, the Sun has gone through stages of formation, starting as a cloud of gas and dust, and eventually collapsing under its own gravity to ignite nuclear fusion. Despite all we know about the Sun, it still presents mysteries. For instance, the solar corona, the outermost layer of the Sun's atmosphere, is much hotter than the surface, a phenomenon that defies the expected behavior of heat dissipation. The influence of the Sun extends far beyond its immediate vicinity. Its gravitational pull keeps all the planets, moons, and other celestial objects in orbit, forming a delicate balance that has persisted for billions of years. The planets themselves are divided into two main categories: terrestrial planets, Mercury, Venus, Earth, and Mars, and gas giants, Jupiter, Saturn, Uranus, and Neptune. Each of these planets has its own unique characteristics, from the sweltering surface of Venus to the gaseous, turbulent atmosphere of Jupiter. The diversity of planetary conditions has led scientists to investigate their formation processes, their evolution, and, in some cases, the possibility of life. Mercury, the smallest planet and the closest to the Sun, has extreme temperature fluctuations due to its lack of atmosphere. Despite its proximity to the Sun, Mercury's surface is not the hottest in the solar system. Venus claims that title due to its thick, greenhouse gas-laden atmosphere. Venus, often called Earth's sister planet because of its similar size and composition, presents a paradoxical landscape. Its surface is a scorched wasteland of high pressure and toxic gases, contrasting starkly with Earth, which sits in the so-called habitable zone, the region around the Sun where conditions are just right for liquid water to exist. Earth, the only known planet to harbor life, offers its own mysteries when viewed from a cosmic perspective. How did life begin here? What are the factors that made Earth so conducive to the formation of life, while Venus and Mars, both of which might have had similar early conditions, ended up so different? These questions continue to fuel research in astrobiology, planetary science, and other disciplines. The unique balance of Earth's atmosphere, magnetic field, and plate tectonics all play a role in maintaining life, but the precise mechanisms that led to these conditions remain an enigma. Mars, the red planet, has long been the subject of fascination for its potential to have once hosted life. The discovery of dried-up riverbeds, polar ice caps, and minerals that form in the presence of water suggest that Mars may have had liquid water on its surface in the past. This opens the door to the tantalizing possibility that microbial life could have existed there. Current missions, such as NASA's Perseverance rover, aim to search for signs of ancient life by examining rocks and soil. But why did Mars lose its atmosphere and water? Why did it become a cold, barren desert when conditions on early Mars might have been similar to those on Earth? These questions highlight the complexity of planetary evolution and how small changes in atmospheric composition or solar radiation can drastically alter a planet's fate. Moving outward from the terrestrial planets, we encounter the gas giants, beginning with Jupiter, the largest planet in the solar system. Jupiter's sheer size and mass exert a significant influence on the solar system, acting as a gravitational shield that deflects many comets and asteroids from colliding with Earth and other inner planets. Its atmosphere is a swirling mass of storms, including the Great Red Spot, a storm larger than Earth that has been raging for centuries. Beneath Jupiter's thick clouds lies a core that scientists believe may be composed of metallic hydrogen, but due to the planet's extreme conditions, understanding its internal structure is challenging. Saturn, with its iconic ring system, is another gas giant that has fascinated observers for centuries. The origin of Saturn's rings remains one of the enduring mysteries of the solar system. Some theories suggest they are remnants of a moon that was torn apart by Saturn's gravity, while others propose that they formed during the planet's formation. Saturn's moons, particularly Titan and Enceladus, are also of great interest. Titan, with its thick atmosphere and lakes of liquid methane, is a world that bears similarities to early Earth and is considered a prime candidate in the search for extraterrestrial life. Enceladus, on the other hand, has a subsurface ocean beneath its icy crust, and plumes of water vapor have been detected erupting from its surface, indicating hydrothermal activity that could support life. Uranus and Neptune, the ice giants, present even more mysteries. Uranus rotates on its side, likely due to a collision with another large object early in its history. This unique tilt causes extreme seasonal variations, and its atmosphere is composed mainly of hydrogen, helium, and methane, giving it a blue-green color. Neptune, the farthest planet from the Sun, is a dynamic world with supersonic winds and large storms, like the Great Dark Spot, which has similarities to Jupiter's Great Red Spot. Both Uranus and Neptune have faint ring systems and numerous moons that continue to be subjects of intense study. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets. One of the most well-known objects in this region is Pluto, which was reclassified as a dwarf planet in 2006. Pluto's status has been a topic of debate among astronomers, but its demotion does not diminish its significance. The New Horizons mission, which flew past Pluto in 2015, revealed a complex and geologically active world with mountains, plains, and glaciers. This challenged the view that small, distant objects are merely frozen remnants of the solar system's formation. The Kuiper Belt also raises questions about the early solar system and the processes that shaped it. Many of the objects in this region are considered to be remnants from the solar system's formation, providing a glimpse into the materials that were present during its early history. Some theories suggest that interactions between the gas giants and the Kuiper Belt could have played a role in shaping the solar system's structure, possibly even contributing to the migration of planets. Beyond the Kuiper Belt lies the hypothetical Oort cloud, a vast sphere of icy objects that is thought to surround the solar system. The Oort cloud is believed to be the source of long-period comets, which take thousands or even millions of years to orbit the Sun. However, no direct observations of the Oort cloud have been made, and its existence remains theoretical. If it does exist, it represents the outermost boundary of the solar system, extending halfway to the nearest star. Understanding the Oort cloud could provide insight into the solar system's interactions with the rest of the galaxy and the forces that govern the distribution of objects in interstellar space. One of the greatest mysteries of the solar system lies in its formation. The prevailing theory is that the solar system formed about 4.6 billion years ago from the gravitational collapse of a giant molecular cloud. But what triggered this collapse? Was it the shock wave from a nearby supernova or some other cosmic event? As the cloud collapsed, it formed a spinning disk of gas and dust, with the Sun at its center. The remaining material coalesced to form the planets, moons, asteroids, and comets. However, the exact mechanisms that led to the formation of different types of planets, particularly the distinction between terrestrial planets and gas giants, are still not fully understood. As the solar system formed from the swirling disk of gas and dust, numerous smaller bodies also came into existence. These objects, ranging from asteroids to comets, have remained largely unchanged since their formation, making them invaluable to scientists trying to understand the early solar system. The asteroid belt, located between Mars and Jupiter, is a region filled with rocky remnants that never coalesced into a planet. This belt contains objects of various sizes, from small rocks to dwarf planets like Ceres. It is thought that the gravitational influence of Jupiter prevented these objects from merging into a larger body. Asteroids can tell us a lot about the composition of the early solar system, as many of them are composed of primitive material that has been relatively undisturbed over billions of years. Ceres, the largest object in the asteroid belt, has drawn attention due to the presence of water ice on its surface. This discovery has raised questions about the potential for water, a key ingredient for life, to exist in unexpected places within the solar system. Could Ceres have harbored life in its past, or does it still have the potential to support life in some form today? These questions reflect a broader inquiry about how common or rare life might be in the universe, and whether the solar system itself might harbor life beyond Earth. Comets are another fascinating group of objects that offer clues about the solar system's past. Unlike asteroids, which are primarily rocky, comets are composed of ice and dust. These icy bodies originate from the distant reaches of the solar system, in regions like the Kuiper Belt and the hypothetical Oort cloud. As comets approach the Sun, their ices vaporize, creating the iconic glowing coma and tail that stretch for millions of kilometers. Comets are believed to be some of the most ancient objects in the solar system, preserving the conditions that existed during its formation. The Rosetta mission, which studied the comet 67P/Churyumov-Gerasimenko, provided a wealth of information about the composition of comets and the role they may have played in delivering water and organic molecules to Earth, possibly seeding the conditions necessary for life. The study of comets also raises questions about the solar system's interactions with other stars. Some scientists believe that the solar system occasionally passes through regions of the galaxy with higher densities of gas and dust, or through the gravitational influence of nearby stars, which could disturb the orbits of comets in the Oort cloud, sending them into the inner solar system. This could explain the occasional influx of comets, known as comet showers, which may have influenced Earth's history, including mass extinction events. The study of moons within the solar system presents another layer of mystery. Earth's moon, for example, is thought to have formed from a colossal impact between Earth and a Mars-sized body early in the solar system's history. This event, known as the giant impact hypothesis, is widely accepted, but there are still questions about the specifics of how this collision unfolded and how it influenced Earth's development. The moon has played a crucial role in stabilizing Earth's axial tilt, which in turn has helped regulate the planet's climate. Without the moon, Earth's seasons might have been far more erratic, making the development of life more difficult. However, the exact details of the moon's influence on Earth's biological and geological evolution are still being studied. Mars' moons, Phobos and Deimos, are another enigma. These small, irregularly shaped bodies are believed to be captured asteroids, but how they were captured remains unclear. Phobos, in particular, is slowly spiraling toward Mars and is expected to either crash into the planet or break apart and form a ring system in the distant future. The origins and fate of these moons provide insight into the dynamic and ever-changing nature of the solar system. Saturn's moon Titan, as mentioned earlier, is another world of great intrigue. With its dense atmosphere and liquid methane lakes, Titan offers a unique environment that could provide clues about the potential for life in environments very different from Earth. The Cassini mission, which studied Saturn and its moons, revealed Titan's complex weather patterns and surface features, including dunes and rivers of methane. Titan is so fascinating that some scientists have proposed future missions to send a submarine to explore its methane lakes, which could lead to the discovery of entirely new forms of chemistry and possibly life. Enceladus, another of Saturn's moons, is equally captivating. Beneath its icy crust lies a subsurface ocean, kept warm by hydrothermal vents at the moon's core. These vents shoot plumes of water vapor and organic molecules into space, And the discovery of such activity has made Enceladus one of the top candidates in the search for extraterrestrial life in the solar system. The potential for life around these vents parallels what we see on Earth, where life thrives around hydrothermal vents in the deep oceans, despite the lack of sunlight. Could similar life forms exist on Enceladus? Future missions are being considered to explore this possibility further. Jupiter's moon Europa is another icy world with a subsurface ocean, and like Enceladus, it has become a prime target in the search for life. Europa's icy surface is crisscrossed by cracks and ridges, suggesting that the ocean beneath is active and interacts with the surface. Tidal forces from Jupiter's strong gravitational pull generate heat within Europa, preventing the ocean from freezing solid. Scientists believe that the ocean could contain more water than all of Earth's oceans combined. If life exists in Europa's ocean, it could be entirely different from anything we know, thriving in an alien environment under thick ice. The exploration of moons like Enceladus, Europa, and Titan highlights the incredible diversity of environments in the solar system. These worlds challenge our understanding of habitability and force us to rethink the conditions under which life could arise. In the past, scientists believed that life required the exact conditions found on Earth: liquid water, an atmosphere, and a temperate climate. But the discovery of extreme environments on Earth, such as deep-sea hydrothermal vents, acidic lakes, and high-radiation environments, has expanded the definition of habitable zones. As we continue to explore the solar system, we may find that life can exist in places we never thought possible. The outer reaches of the solar system, beyond the known planets and moons, continue to harbor mysteries. For example, astronomers have hypothesized the existence of a ninth planet, often referred to as Planet 9 or Planet X, based on the strange orbits of distant objects in the Kuiper Belt. These objects, known as trans-Neptunian objects, TNOs, exhibit orbits that are not easily explained by the gravitational influence of the known planets. Some scientists believe that a large, undiscovered planet, much farther from the Sun than Neptune, could be influencing these orbits. If Planet 9 exists, it would have a mass several times that of Earth and an orbit that takes it far beyond the outer reaches of the solar system. However, no direct evidence of such a planet has been found yet, and its existence remains speculative. The search for Planet 9 is part of a broader effort to understand the dynamics of the outer solar system, where many objects remain undiscovered. The Kuiper Belt and Oort cloud are thought to contain trillions of icy bodies, some of which may harbor clues about the formation of the solar system and its interactions with other stars. These distant objects, many of which are too faint to be detected with current technology, represent the frontier of solar system exploration. One of the most intriguing aspects of the solar system is the question of its ultimate fate. The Sun, like all stars, will eventually exhaust its supply of nuclear fuel. When this happens, the Sun will enter the red giant phase, expanding to engulf the inner planets, including Earth. After shedding its outer layers, the Sun will become a white dwarf, slowly cooling over billions of years. What will happen to the rest of the solar system during this process? Will any planets survive the Sun's transformation, or will they be ejected into interstellar space? Could moons like Titan or Europa, far from the Sun's influence, become more habitable as the Sun expands and heats them? These long-term questions about the solar system's future are complemented by more immediate concerns, such as the potential for asteroid impacts. Throughout Earth's history, impacts from asteroids and comets have caused mass extinctions and dramatic changes in the planet's climate. The most famous example is the impact that is believed to have caused the extinction of the dinosaurs 66 million years ago. While such large impacts are rare, they are not impossible. Astronomers continue to monitor near-Earth objects, NEOs, that could pose a threat to our planet, and efforts are underway to develop technologies that could deflect or destroy an incoming asteroid. As the monitoring of near-Earth objects, NEOs, continues, humanity remains alert to the possibility of future impacts. Programs like NASA's Planetary Defense Coordination Office have been established to track these objects, calculate their trajectories, and determine if any might pose a threat to Earth. One of the key technologies being developed is the ability to deflect an asteroid, either by using a spacecraft to nudge it off course or by detonating an explosive nearby to alter its path. The Double Asteroid Redirection Test (DART) mission, launched by NASA, aims to test such a technique by intentionally crashing into the asteroid Didymos to slightly alter its orbit. While the likelihood of a catastrophic impact is low, the potential consequences are so severe that scientists view planetary defense as a crucial area of research. In addition to potential impacts, space weather also poses a threat to the solar system, particularly Earth. Space weather refers to the environmental conditions in space, including solar radiation, solar wind, and magnetic fields. Solar flares and coronal mass ejections, CMEs, massive bursts of solar wind and magnetic fields from the sun, can have dramatic effects on Earth. These events can cause disruptions to satellite communications, GPS systems, and power grids. In 1859, a massive solar storm known as the Carrington event caused widespread electrical disruptions, and if a similar event were to occur today, the damage to modern infrastructure could be far more severe. Understanding and predicting solar activity is vital to safeguarding the technology-dependent societies of the modern world. The study of solar activity also raises questions about the long-term stability of the sun and its effects on the solar system. While the sun has been relatively stable for billions of years, it is not entirely predictable. Solar cycles, which occur approximately every 11 years, cause fluctuations in solar activity, with periods of increased sunspot formation and solar storms. The exact causes and mechanics of these cycles remain poorly understood, but scientists continue to study the sun's magnetic field and plasma dynamics to improve predictions. The exploration of the solar system has also led to a deeper understanding of the complex interplay between gravity, magnetism, and the fundamental forces that govern planetary systems. For example, the discovery of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, has revolutionized our understanding of the universe. While gravitational waves were first detected in 2015 from colliding black holes, their presence also has implications for solar system dynamics. The study of gravitational waves could one day provide new insights into how the solar system formed and how its structure may evolve. In addition to gravity, magnetism plays a crucial role in the behavior of many solar system objects. Earth's magnetic field, generated by the motion of molten iron in its core, protects the planet from harmful solar and cosmic radiation. This magnetic shield deflects charged particles from the sun, creating phenomena like the auroras, northern and southern lights, when these particles interact with Earth's atmosphere. However, Earth's magnetic field is not constant. It undergoes periodic reversals, where the magnetic poles switch places. The last reversal occurred about 780,000 years ago, and scientists believe we are overdue for another one. While a magnetic reversal would not necessarily be catastrophic, it could temporarily weaken the planet's magnetic field, making Earth more vulnerable to solar radiation. Magnetism is also significant in the context of other planets. Jupiter, for example, has the strongest magnetic field of any planet in the solar system, extending millions of kilometers into space and creating intense radiation belts around the planet. These belts pose a significant hazard to spacecraft and any potential future missions to Jupiter's moons, such as Europa. The origin of Jupiter's magnetic field is linked to the planet's internal structure, where liquid metallic hydrogen generates a powerful dynamo effect. Understanding how such fields are generated and how they evolve over time is a key area of research, not just for planetary science, but also for understanding the broader workings of the universe. Saturn's magnetic field, while weaker than Jupiter's, is still impressive. Its interactions with the planet's rings and moons create complex electromagnetic environments. For instance, Saturn's moon Enceladus, which ejects plumes of water vapor into space, interacts with the planet's magnetic field, generating a thin layer of ionized gas around Saturn. This interaction is just one example of the intricate connections between solar system objects, demonstrating that even seemingly isolated bodies can have far-reaching effects on their surroundings. The search for life in the solar system has expanded far beyond Earth, and scientists are now investigating the potential for life to exist in environments very different from our own. Mars, with its dry, dusty surface, has long been a candidate for life, particularly in its distant past when liquid water was more abundant. Robotic missions like the Perseverance rover are actively searching for signs of ancient microbial life by studying the geology of Mars, analyzing rock samples, and searching for biosignatures, chemical indicators of past life. If life once existed on Mars, its discovery would not only revolutionize our understanding of biology but also provide new insights into the conditions necessary for life to emerge. But the search for life is not limited to Mars. As mentioned earlier, the icy moons of the outer planets, such as Europa and Enceladus, are also prime candidates for extraterrestrial life. These moons, with their subsurface oceans, offer environments where life could potentially thrive, protected from the harsh radiation of space by thick ice layers. Future missions, such as the Europa Clipper, are designed to study these moons in greater detail, searching for signs of life or conditions that could support it. These missions could ultimately answer one of the most profound questions of all: are we alone in the universe? In addition to searching for life within the solar system, scientists are also interested in understanding the potential habitability of other planets and moons. Venus, often considered Earth's twin because of its similar size and proximity to the Sun, has long been regarded as inhospitable due to its extreme temperatures and thick, toxic atmosphere. However, recent studies have suggested that Venus may have once had liquid water on its surface and could have supported life billions of years ago. Some scientists even speculate that life could still exist in the upper layers of Venus's atmosphere, where conditions are less extreme. The discovery of phosphine, a possible biosignature gas, in Venus's atmosphere sparked renewed interest in the planet, although the detection remains controversial and more research is needed. While the solar system offers a wealth of opportunities for exploration and discovery, it also presents significant challenges. One of the biggest obstacles to further exploration is the vast distances between planets and moons. Even with modern spacecraft, it takes years to reach the outer planets. The Voyager missions, launched in the 1970s, took more than a decade to reach Neptune, and they are now traveling through interstellar space beyond the influence of the Sun's gravity. Future missions to distant objects like Pluto, the Kuiper Belt, and the Oort cloud will require new technologies to reduce travel time and increase the range of exploration. Another challenge is the harsh environment of space itself. Solar radiation, cosmic rays, and the vacuum of space pose significant risks to both human explorers and robotic spacecraft. Spacecraft must be carefully designed to withstand these conditions, and any future human missions to Mars or beyond will require advanced life support systems and radiation shielding to protect astronauts. The development of new propulsion technologies, such as nuclear thermal propulsion or ion drives, could also help overcome some of the challenges of space travel by reducing travel time and increasing the efficiency of spacecraft. The solar system is a dynamic and ever-changing place, and our understanding of it is constantly evolving. As new discoveries are made, old mysteries are solved, and new questions arise. The exploration of the solar system has transformed our understanding of the universe and our place in it. From the birth of the Sun and the planets to the potential for life on other worlds, the solar system holds the key to many of the most profound mysteries of existence. The study of the solar system also forces us to confront the fragility of life on Earth. While Earth has been remarkably stable for billions of years, it is not immune to the forces that shape the rest of the solar system. Asteroid impacts, solar storms, and other cosmic events could have dramatic consequences for life on Earth. Understanding these risks and developing strategies to mitigate them is an essential part of the ongoing exploration of the solar system. The exploration of the solar system also raises philosophical and existential questions about humanity's future. As we continue to explore the planets, moons, and other celestial bodies, we are forced to consider what it means to be an interplanetary species. The dream of colonizing Mars, for example, has captivated scientists, engineers, and visionaries for decades. Mars offers the closest thing to a second home in the solar system, with its relatively mild conditions compared to other planets, the presence of water ice, and the possibility of utilizing its resources to support human life. However, the challenges of living on Mars are immense. The thin atmosphere provides little protection from cosmic radiation, temperatures are frigid, and the lack of oxygen and liquid water means that any future colonists would need to bring or produce everything they need to survive. The concept of terraforming, altering Mars' environment to make it more Earth-like, has been proposed as a long-term solution for making the planet habitable. This process would involve releasing greenhouse gases into the Martian atmosphere to warm the planet and create conditions that could support liquid water. While the idea of transforming an entire planet is appealing, the technical and ethical challenges are daunting. The amount of time and resources required would be astronomical, and there are questions about whether it is right to alter a pristine, extraterrestrial environment. Beyond Mars, the idea of colonizing other moons and planets within the solar system becomes even more speculative. Europa, with its subsurface ocean, is often cited as a candidate for future colonization, though living beneath kilometers of ice in an ocean with no atmosphere poses challenges far greater than Mars. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane, but the extreme cold would require new technologies for survival. The idea of living on floating habitats in the clouds of Venus, where conditions are more Earth-like at certain altitudes, has also been proposed. Each of these ideas highlights the creativity and ambition of humanity, but they also emphasize just how hostile and unforgiving most of the solar system is. The solar system is not just a place for human exploration and colonization, it is also a laboratory for understanding fundamental questions about the nature of the universe. The study of planetary systems, their formation, and evolution can provide insights into how planets form around other stars. By understanding the processes that shaped our solar system, we can better understand the thousands of exoplanets that have been discovered in recent years. The discovery of exoplanets, planets orbiting stars other than the Sun, has opened up new possibilities for the search for life beyond the solar system. Some of these exoplanets are located in the so-called habitable zone, where conditions might be right for liquid water and, potentially, life. The search for exoplanets has been greatly aided by missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, which have discovered thousands of planets by monitoring stars for tiny dips in brightness caused by planets passing in front of them. As technology improves, future missions will be able to directly image exoplanets, analyze their atmospheres, and potentially detect signs of life. While the discovery of life on an exoplanet would be a monumental achievement, the challenges of exploring these distant worlds are far greater than those of exploring our own solar system. The vast distances between stars mean that any direct exploration would require new propulsion technologies, such as faster-than-light travel, which remains firmly in the realm of science fiction for now. In the meantime, the mysteries of the solar system continue to captivate scientists and the public alike. The question of whether life exists elsewhere in the solar system, either on Mars, Europa, or another body, remains one of the most profound questions in science. The potential discovery of life, even microbial life, would have far-reaching implications for our understanding of biology, the origins of life, and the likelihood of life elsewhere in the universe. The search for life is also closely tied to the study of water in the solar system. Water is essential for life as we know it, and the discovery of water in unexpected places, such as the poles of the Moon, the underground lakes of Mars, and the plumes of Enceladus, has renewed interest in these worlds. Understanding how water is distributed throughout the solar system, how it got there, and whether it could support life is a key area of research. Water ice has been found on Mercury, the closest planet to the Sun, and permanently shadowed craters at the planet's poles, where temperatures are low enough for ice to remain stable. This discovery was surprising given Mercury's proximity to the Sun, but it demonstrates the diverse range of environments that exist within the solar system. The study of water and other volatile substances, such as methane and ammonia, is also critical for understanding the chemistry of planets and moons. These substances can reveal information about the history and evolution of planetary bodies. For example, the methane detected on Titan and Mars raises questions about whether it is produced by geological processes or biological activity. On Earth, most methane is produced by living organisms, but it can also be produced by chemical reactions in the subsurface. Determining the source of methane on other planets could provide clues about the potential for life or the presence of active geological processes. As we look to the future of solar system exploration, one of the most exciting prospects is the possibility of sample return missions. While robotic spacecraft have provided invaluable data, there is no substitute for analyzing samples directly in laboratories on Earth. NASA's Perseverance rover is collecting rock samples on Mars with the goal of returning them to Earth in the 2030s. This mission could provide the first direct evidence of whether life ever existed on Mars. Similarly, missions to asteroids, such as Japan's Hayabusa 2 and NASA's OSIRIS-RX, have successfully returned samples from these small bodies, offering insights into the early solar system and the building blocks of planets. Asteroids and comets, often considered the leftover debris from the solar system's formation, hold key information about the conditions that existed in the early solar system. Studying these objects can help scientists understand how planets formed and evolved, as well as the role these small bodies played in delivering water and organic compounds to Earth. Some scientists believe that comets or asteroids could have been responsible for delivering the ingredients necessary for life to emerge on Earth, a theory known as panspermia. Panspermia suggests that life could be distributed throughout the universe by comets, asteroids, or even dust particles. While there is no direct evidence to support this theory, it remains an intriguing possibility. If life did originate elsewhere in the solar system and was delivered to Earth, it would raise profound questions about the nature of life and its distribution in the cosmos. Alternatively, if life emerged independently on Earth and elsewhere in the solar system, it would suggest that life is more common in the universe than previously thought. As scientists continue to explore the solar system, they are also grappling with the challenges of protecting these environments from contamination. Planetary protection is a critical aspect of space exploration, ensuring that missions do not introduce Earth-based organisms to other worlds and that any potential life on those worlds is not contaminated by human activity. This is particularly important for missions to Mars, Europa, and other bodies where life might exist. The introduction of Earth microbes could interfere with the search for extraterrestrial life and compromise scientific findings. NASA and other space agencies follow strict protocols to sterilize spacecraft and limit the potential for contamination. Planetary protection is also a consideration for future human missions. While robotic missions can be carefully controlled, humans inevitably carry microorganisms with them. Ensuring that human explorers do not inadvertently contaminate other worlds will be a significant challenge, especially if humans are to live and work on Mars or other planets for extended periods. The mysteries of the solar system extend beyond the search for life and the exploration of planets and moons. The study of the Sun, the dynamics of planetary orbits, and the behavior of comets and asteroids all contribute to our understanding of the forces that govern the universe. The solar system is a microcosm of the broader universe, providing a laboratory for studying fundamental processes such as gravity, magnetism, and the interactions between matter and energy. The Sun, at the heart of the solar system, is one of the most studied yet mysterious objects. As a G-type main sequence star, it generates energy through nuclear fusion, converting hydrogen into helium in its core. This process releases enormous amounts of energy in the form of light and heat, making life on Earth possible. The Sun's influence extends far beyond its immediate vicinity. Its gravitational pull keeps the planets in orbit, and its solar wind, a stream of charged particles, interacts with planetary magnetospheres, shaping space weather throughout the solar system. Despite the Sun's critical role, there are still many unanswered questions about its behavior. One of the most significant mysteries is the solar cycle, an approximately 11-year cycle during which the Sun's magnetic activity increases and decreases. During periods of high activity, known as solar maximum, the Sun's surface is covered with sunspots, dark, cooler regions caused by intense magnetic fields. These periods are also marked by powerful solar flares and coronal mass ejections, which can send massive amounts of charged particles into space. These events can have significant effects on Earth, disrupting communication satellites, damaging power grids, and creating spectacular auroras near the poles. However, the underlying mechanisms that drive the solar cycle are not fully understood. Scientists know that the Sun's magnetic field is responsible for the cycle, but predicting the timing and intensity of solar maximums and minimums remains challenging. Understanding the solar cycle is not just an academic exercise, it has practical implications for space exploration and the protection of infrastructure on Earth. As human activity in space increases, the need to predict and mitigate the effects of solar storms becomes more pressing. Future space missions to the Moon, Mars, and beyond will need to take into account the dangers posed by solar radiation and charged particles. Another mystery of the Sun is its outer atmosphere, or corona. The corona is much hotter than the Sun's surface, with temperatures reaching millions of degrees Celsius. This is counterintuitive, as one would expect the outer layers of a star to be cooler than the surface, yet the corona is many times hotter. The exact mechanism responsible for heating the corona remains an open question, although scientists believe that the Sun's magnetic field plays a role. One hypothesis is that magnetic reconnection, where magnetic field lines snap and release energy, could be responsible for heating the corona. Understanding the behavior of the corona is also important for predicting solar storms, as coronal mass ejections originate in these outer layers. The study of the solar wind, the stream of charged particles released by the Sun, is another area of ongoing research. The solar wind extends far beyond the orbit of Pluto, forming a bubble around the solar system known as the heliosphere. This bubble protects the solar system from much of the cosmic radiation that exists in interstellar space. However, the boundary of the heliosphere is not static. As the solar wind interacts with the interstellar medium, the shape and size of the heliosphere change. NASA's Voyager 1 and 2 spacecraft, which have now entered interstellar space, are providing valuable data on the heliosphere's outer boundary, known as the heliopause. These spacecraft are the first to provide direct measurements of the conditions in interstellar space, giving scientists new insights into the environment beyond the solar system. While the Sun dominates the solar system, the planets themselves also hold many mysteries. Mercury, the closest planet to the Sun, is a small, rocky world with a surface marked by craters and cliffs. Despite its proximity to the Sun, Mercury has water ice and permanently shadowed craters at its poles, where temperatures are low enough for ice to remain stable. How water ice ended up on Mercury is still debated. Some scientists believe it was delivered by comets or asteroids, while others suggest that it could have been produced by chemical reactions involving the planet's thin atmosphere. Understanding the origin of this ice could provide clues about the history of water in the inner solar system. Venus, often called Earth's twin because of its similar size and composition, presents one of the most extreme environments in the solar system. Its thick atmosphere, composed mostly of carbon dioxide, creates a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius, hot enough to melt lead. The surface pressure on Venus is also more than 90 times that of Earth, making it an incredibly hostile environment. Despite these extreme conditions, there is evidence that Venus may have once had a more Earth-like climate, with liquid water on its surface. What caused Venus to become the scorching world it is today remains a topic of intense study. The possibility that Venus experienced a climate catastrophe could provide important lessons for understanding climate change on Earth. There is also the tantalizing possibility that microbial life could exist in the upper atmosphere of Venus, where temperatures and pressures are much more moderate. In 2020, scientists announced the detection of phosphine gas in Venus's atmosphere, a chemical that, on Earth, is associated with biological activity. While the discovery is still being debated, it has reignited interest in the possibility of life on Venus. Future missions, such as NASA's Veritas and Europe's Envision, aim to study Venus's atmosphere and surface in more detail, potentially shedding light on this enduring mystery. Earth itself, while familiar, still holds many mysteries when viewed in the context of the solar system. Our planet is unique in the solar system for its abundance of liquid water, diverse climate, and the presence of life. One of the biggest questions in planetary science is how Earth's environment became so conducive to life. The presence of a stable climate, a magnetic field that protects the planet from solar radiation, and plate tectonics that recycle nutrients are all factors that contribute to Earth's habitability. Yet, why Earth developed these conditions while Venus and Mars did not is still not fully understood. Mars, often called the Red Planet, has captivated human imagination for centuries. The discovery of water ice deposits, evidence of ancient river valleys, and seasonal methane emissions have fueled speculation about the possibility of life on Mars, either in the past or present. The search for life on Mars is one of the primary goals of missions like NASA's Perseverance rover, which is exploring an ancient lakebed in the Jezero crater, searching for signs of past microbial life. While the surface of Mars today is cold, dry, and barren, there is evidence that it once had a much thicker atmosphere, liquid water, and possibly even oceans. What caused Mars to lose its atmosphere and water remains an open question, but the planet's small size and lack of a magnetic field are likely contributing factors. Jupiter, the largest planet in the solar system, is a gas giant composed mostly of hydrogen and helium. Its massive size and strong gravitational pull have a profound influence on the rest of the solar system. Jupiter's gravity has helped shape the orbits of many smaller bodies, including asteroids and comets, and it acts as a cosmic vacuum cleaner, capturing or deflecting objects that might otherwise pose a threat to Earth. Despite its size, Jupiter's interior remains a mystery. It is believed to have a small, rocky core surrounded by a thick layer of metallic hydrogen, but direct observations of the planet's interior are difficult. Jupiter's magnetic field is also the strongest in the solar system, producing powerful auroras at the planet's poles. Jupiter is also home to some of the most fascinating moons in the solar system, including Ganymede, the largest moon, which has its own magnetic field, and Europa, which is believed to have a subsurface ocean beneath its icy crust. Europa is one of the prime candidates for the search for extraterrestrial life, as its ocean may have the right conditions to support microbial life. NASA's upcoming Europa Clipper mission will study the moon in detail, looking for signs of habitability and potentially even direct evidence of life. Saturn, with its iconic ring system, is another gas giant that continues to intrigue scientists. The origin of Saturn's rings is still debated. Some believe they formed from the debris of a shattered moon, while others think they may be remnants of the early solar system. Saturn's moon Titan, the second largest moon in the solar system, is another world of interest. Titan has a thick atmosphere, lakes of liquid methane, and a complex weather system. While it is far too cold for liquid water to exist on Titan's surface, the presence of liquid methane and the discovery of complex organic molecules make it an intriguing candidate for the search for life. NASA's Dragonfly mission, scheduled to launch in the mid-2020s, will explore Titan's surface, looking for clues about the chemistry of life and the moon's potential habitability. Uranus, the seventh planet from the Sun, is one of the least understood in the solar system. Unlike the gas giants Jupiter and Saturn, Uranus is classified as an ice giant because it contains a higher proportion of icy materials like water, ammonia, and methane. These materials give Uranus its characteristic blue-green color. One of the most peculiar features of Uranus is its extreme axial tilt. The planet is tilted on its side, with its axis of rotation nearly parallel to its orbit around the Sun. This means that Uranus experiences extreme seasonal variations, with each pole getting 42 years of continuous sunlight followed by 42 years of darkness. The cause of this extreme tilt is thought to be a collision with a large object early in the planet's history, but this remains speculative. Uranus's interior is largely a mystery. It is believed to have a rocky core surrounded by icy materials and a thick atmosphere composed mostly of hydrogen and helium. However, Uranus radiates very little heat, which sets it apart from the other giant planets. Most planets radiate more heat than they receive from the Sun, but Uranus does not, and scientists are still unsure why. Another mystery lies in the planet's magnetic field, which is both tilted and offset from its center. This suggests that the magnetic field may be generated in a layer of the planet that is closer to the surface than in other planets, but the exact mechanism remains unclear. Uranus has 27 known moons, and many of these moons show signs of interesting geological activity. For example, Miranda, one of the smallest moons of Uranus, has some of the most dramatic surface features in the solar system, including giant canyons and terraced structures. These features suggest that Miranda may have undergone intense geological upheavals in the past, but the cause of this activity is still not fully understood. Some scientists speculate that gravitational interactions with Uranus or its other moons could have triggered the resurfacing events on Miranda. Neptune, the outermost planet in the solar system, is similar to Uranus in many ways, but it also has its unique mysteries. Like Uranus, Neptune is classified as an ice giant, with a composition that includes water, ammonia, and methane. Neptune's striking blue color comes from the absorption of red light by methane in its atmosphere, but the exact mechanism that creates the planet's intense blue hue is not entirely understood. One of the most intriguing aspects of Neptune is its weather. The planet has some of the most extreme weather in the solar system, with wind speeds reaching up to 2,000 kilometers per hour. These winds are the fastest observed on any planet, but how they are generated and maintained remains a mystery. Neptune is much farther from the Sun than the other planets, and it receives very little solar energy, yet its atmosphere is more dynamic than those of the inner planets. Neptune also has a complex magnetic field, which, like Uranus's, is tilted and offset from the planet's center. The magnetic fields of Uranus and Neptune are thought to be generated by processes that are different from those in other planets, but the details of these processes are still not fully understood. Neptune has 14 known moons, the largest of which is Triton. Triton is unique in the solar system because it orbits Neptune in the opposite direction of the planet's rotation, a phenomenon known as a retrograde orbit. This suggests that Triton was likely captured by Neptune's gravity and did not form alongside the planet. Triton's surface is covered in a thin layer of nitrogen ice, and it has active geysers that spew nitrogen gas into space, making it one of the few places in the solar system where active geological processes have been observed. Triton is also of interest in the search for extraterrestrial life because it is believed to have a subsurface ocean beneath its icy crust. Like Europa and Enceladus, moons that are believed to have subsurface oceans, Triton's ocean could potentially harbor microbial life. However, the conditions on Triton are extremely harsh, with surface temperatures dropping to -235 degrees Celsius, making it one of the coldest objects in the solar system. Despite these challenges, future missions to Triton could provide valuable insights into the potential for life in the outer solar system. Pluto, which was reclassified as a dwarf planet in 2006, lies beyond Neptune in the region known as the Kuiper Belt. The Kuiper Belt is a vast, icy region of the solar system that contains many small, frozen bodies, including Pluto and its moon Charon. Despite its small size, Pluto has proven to be a complex and dynamic world. NASA's New Horizons mission, which flew by Pluto in 2015, revealed that the dwarf planet has a surprisingly varied surface, with large plains of nitrogen ice, towering mountains made of water ice, and possible cryovolcanoes that may have erupted with icy slush. One of the most striking features of Pluto is its heart-shaped region, and formerly known as Tombaugh Regio. This region is made of nitrogen ice and is believed to be geologically active, with surface features that suggest the ice is flowing like glaciers on Earth. How Pluto remains geologically active, despite being so far from the Sun, is still a mystery. Some scientists believe that Pluto's interior may be warmer than previously thought, possibly due to the presence of radioactive elements that generate heat as they decay. Another possibility is that tidal interactions with Charon, Pluto's largest moon, may be generating heat and driving geological processes. Pluto's atmosphere is also of interest to scientists. It is composed mainly of nitrogen, with traces of methane and carbon monoxide, and it undergoes dramatic changes as Pluto moves through its 248-year orbit around the Sun. When Pluto is closer to the Sun, its atmosphere expands as the surface ice sublimates into gas. As Pluto moves farther from the Sun, the atmosphere freezes and falls back to the surface. This seasonal behavior is unique in the solar system, and future observations of Pluto could provide new insights into the dynamics of thin atmospheres on icy worlds. Beyond Pluto lies the vast, mysterious realm of the Kuiper Belt and the even more distant Oort cloud. The Kuiper Belt is home to many small, icy objects, some of which are thought to be remnants from the early solar system. Studying these objects could provide valuable clues about the formation of the solar system and the processes that shaped its evolution. The Oort cloud, which is believed to surround the solar system at a distance of up to 100,000 astronomical units, is the source of long-period comets. These comets, which take hundreds or even thousands of years to complete an orbit around the Sun, are some of the most distant objects in the solar system, and their origins are still poorly understood. One of the biggest mysteries of the solar system is the formation of the planets themselves. While the basic process of planetary formation, accretion from a protoplanetary disk of gas and dust, is well understood, many details remain uncertain. For example, why are the inner planets small and rocky while the outer planets are gas giants? How did the giant planets acquire their massive atmospheres of hydrogen and helium? And what caused the migration of planets early in the solar system's history, which may have reshaped the orbits of smaller bodies and caused the Late Heavy Bombardment, a period of intense meteorite impacts about 4 billion years ago? The migration of planets is a relatively new concept in planetary science, and it has reshaped our understanding of the solar system's early history. According to the NICE model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed much closer to the Sun than they are today. Over time, gravitational interactions between the planets and the surrounding disk of gas and dust caused them to migrate outward. As they moved, they scattered smaller bodies, some of which became the asteroids and comets we see today. The Late Heavy Bombardment, a period when the inner planets were bombarded by a large number of meteorites, may have been triggered by this migration. The Late Heavy Bombardment, which occurred about 4 billion years ago, left a significant mark on the inner planets, including Earth, the Moon, and Mars. During this period, a large number of asteroids and comets were sent careening through the inner solar system, causing widespread impacts. Evidence of this bombardment is visible on the surfaces of the Moon and Mars, which are covered with craters from this time. On Earth, however, the evidence has largely been erased by geological processes such as plate tectonics and erosion, although some ancient impact craters have been preserved. The cause of the late heavy bombardment remains a mystery, but many scientists believe it was triggered by the migration of the outer planets. As Jupiter and Saturn moved outward, their gravity could have disturbed the orbits of smaller bodies in the asteroid belt and Kuiper belt, sending them on collision courses with the inner planets. This period of intense impacts may have played a role in shaping the development of life on Earth, as the impacts could have delivered water and organic molecules to the planet. One of the most interesting aspects of the late heavy bombardment is its potential connection to the origins of life on Earth. Some scientists believe that comets and asteroids, which are rich in water and organic molecules, may have been responsible for delivering the building blocks of life to Earth during this period. This idea, known as panspermia, suggests that life on Earth may have originated from materials that were brought here from elsewhere in the solar system or even from other star systems. While this idea remains speculative, it highlights the interconnectedness of the solar system and the role that cosmic events may have played in the development of life. Another mystery of the solar system is the role of Jupiter in protecting the inner planets. Jupiter is the largest planet in the solar system, and its massive gravity has a significant influence on the orbits of other bodies. Some scientists believe that Jupiter acts as a kind of shield, protecting the inner planets from frequent asteroid impacts by diverting or capturing objects that might otherwise collide with Earth. However, Jupiter's role is not entirely protective. In some cases, its gravity can send comets and asteroids toward the inner solar system, increasing the likelihood of impacts. The asteroid belt, located between Mars and Jupiter, is another region of the solar system that holds many mysteries. The belt contains a vast number of rocky objects, ranging in size from small pebbles to the dwarf planet Ceres. For many years, scientists believed that the asteroid belt represented the remains of a planet that never formed. However, more recent research suggests that the material in the asteroid belt may have been prevented from coalescing into a planet by the gravitational influence of Jupiter. The exact processes that shaped the asteroid belt and its evolution over time are still not fully understood, but studying this region could provide valuable insights into the early history of the solar system. Ceres, the largest object in the asteroid belt, is classified as a dwarf planet, and it has its own set of mysteries. Observations from NASA's Dawn mission revealed that Ceres has bright spots on its surface, which are believed to be deposits of salt left behind by sublimating water ice. This suggests that Ceres may have a subsurface ocean, similar to other icy bodies in the solar system. The presence of water on Ceres raises the intriguing possibility that this dwarf planet could harbor microbial life, although no direct evidence of life has been found so far. The study of asteroids and comets is important not only for understanding the history of the solar system but also for protecting Earth from potential future impacts. Several asteroids have been identified as potentially hazardous objects, meaning that their orbits bring them close to Earth and there is a small chance that they could collide with our planet in the future. NASA and other space agencies are actively monitoring these objects and developing strategies for deflecting or mitigating the impact of any asteroid that might be on a collision course with Earth. In 2022, NASA successfully demonstrated the potential for asteroid deflection with its DART, Double Asteroid Redirection Test, mission. The mission aimed to change the orbit of a small asteroid by intentionally crashing a spacecraft into it. This test was the first real-world demonstration of a planetary defense strategy and could pave the way for future efforts to protect Earth from dangerous asteroids. Moving farther out into the solar system, the region beyond Neptune is known as the Kuiper belt, which is home to many small, icy objects. The Kuiper belt is a remnant of the early solar system, and it contains objects that have remained largely unchanged for billions of years. Studying these objects could provide valuable insights into the conditions that existed in the early solar system and the processes that led to the formation of the planets. One of the most famous objects in the Kuiper Belt is Pluto, which was reclassified as a dwarf planet in 2006. Pluto was once considered the ninth planet in the solar system, but the discovery of other large objects in the Kuiper Belt led scientists to rethink its classification. Despite its small size, Pluto has proven to be a fascinating and complex world. NASA's New Horizons mission, which flew by Pluto in 2015, revealed a world with a surprisingly diverse landscape, including towering mountains made of water ice, vast plains of nitrogen ice, and possible cryovolcanoes. Pluto's atmosphere is also of great interest to scientists. It is composed mainly of nitrogen, with traces of methane and carbon monoxide, and it undergoes dramatic changes as Pluto moves through its elliptical orbit around the Sun. When Pluto is closer to the Sun, its atmosphere expands as the surface ice sublimates into gas. As Pluto moves farther from the Sun, the atmosphere freezes and falls back to the surface. This seasonal behavior is unique in the solar system, and future observations of Pluto could provide new insights into the dynamics of thin atmospheres on icy worlds. Charon, Pluto's largest moon, is another intriguing object in the Kuiper Belt. Charon is about half the size of Pluto, making it one of the largest moons in the solar system relative to its parent planet. Charon's surface shows signs of past geological activity, including large canyons and fractures that suggest the moon may have undergone significant tectonic processes in the past. Some scientists believe that Charon may have once had a subsurface ocean, which could explain the tectonic features observed on its surface. Beyond Pluto, the Kuiper Belt extends for billions of kilometers, and it contains many other small, icy bodies that have yet to be fully explored. One of the most interesting of these objects is Eris, another dwarf planet that is similar in size to Pluto. Eris was discovered in 2005, and its discovery was one of the key factors that led to the reclassification of Pluto as a dwarf planet. Like Pluto, Eris has a highly elliptical orbit, and it takes about 558 years to complete one orbit around the Sun. Little is known about the surface of Eris, but future missions to the Kuiper Belt could provide valuable insights into this distant world. The Kuiper Belt is also home to many smaller objects, some of which have been visited by spacecraft. In 2019, NASA's New Horizons mission flew by a Kuiper Belt object known as Arrokoth, which is one of the most distant objects ever explored by a spacecraft. Arrokoth is a contact binary, meaning that it consists of two smaller objects that have merged together. The surface of Arrokoth is covered in red organic materials, and its shape and composition provide clues about the processes that shaped the early solar system. Far beyond the Kuiper Belt lies the Oort cloud, a hypothetical region that is thought to contain trillions of icy bodies. The Oort cloud is the source of long-period comets, which take hundreds or even thousands of years to complete an orbit around the Sun. These comets are some of the most distant objects in the solar system, and their origins are still poorly understood. Some scientists believe that the Oort cloud may contain objects that were scattered out of the inner solar system by the migration of the giant planets, while others think that it may contain material that was captured from other star systems. One of the biggest mysteries of the solar system is the question of whether there is life beyond Earth. The discovery of life elsewhere in the solar system would be one of the most profound scientific discoveries of all time, and scientists have been searching for signs of life on other planets and moons for decades. While no direct evidence of extraterrestrial life has been found so far, several places in the solar system are considered promising candidates for life. Mars has long been a focus of the search for life, and recent discoveries suggest that the red planet may have once had conditions that were suitable for life. Evidence of ancient rivers, lakes, and even oceans has been found on Mars, and the planet's surface is covered with minerals that form in the presence of water. In addition, recent missions have detected traces of methane in the Martian atmosphere, which could be a sign of microbial life. However, methane can also be produced by geological processes, so its presence does not necessarily indicate life. The search for microbial life on Mars continues with ongoing missions, such as NASA's Perseverance rover and the European Space Agency's ExoMars mission. Perseverance is equipped with advanced scientific instruments designed to analyze soil and rock samples for signs of ancient microbial life. It is also tasked with collecting samples that will eventually be returned to Earth for further study, potentially providing US with a clearer picture of Mars' history and its habitability. Another intriguing body in the solar system is Europa, one of Jupiter's moons. Europa is covered in a thick layer of ice, and beneath this icy shell, scientists believe there may be a vast ocean of liquid water. This subsurface ocean is thought to be in contact with Europa's rocky mantle, creating the potential for chemical interactions that could support life. Several missions are planned to explore Europa in more detail, including NASA's upcoming Europa Clipper mission, which aims to investigate the moon's ice shell, subsurface ocean, and potential for habitability. Similarly, Enceladus, one of Saturn's moons, has garnered significant interest from scientists due to its geysers that eject water vapor and ice particles into space. The Cassini spacecraft, which studied Saturn and its moons from 2004 to 2017, discovered these plumes, providing compelling evidence of a subsurface ocean beneath Enceladus' icy surface. The presence of organic compounds in the plumes raises the intriguing possibility that this moon could harbor life, and future missions may seek to analyze the material ejected from Enceladus for signs of biological activity. Titan, another of Saturn's moons, presents a unique environment that is unlike any other in the solar system. It is the only moon with a thick atmosphere, primarily composed of nitrogen, and surface lakes and rivers of liquid methane and ethane. The chemistry on Titan is vastly different from that on Earth, yet it offers a tantalizing glimpse into alternative forms of chemistry that could lead to life. The upcoming Dragonfly mission, which is set to launch in the mid-2030s, will send a rotorcraft to Titan to explore its diverse landscapes and investigate its potential for habitability. As we explore these celestial bodies, we also confront fundamental questions about the nature of life itself. What are the conditions necessary for life to arise? Can life exist in extreme environments, such as the subsurface oceans of icy moons or the methane lakes of Titan? The answers to these questions could reshape our understanding of life's origins and its potential existence beyond Earth. Beyond the potential for life, the solar system is full of intriguing phenomena that challenge our understanding of physics and astronomy. One such mystery involves the magnetic fields of various celestial bodies. For instance, Earth has a strong magnetic field generated by the motion of molten iron in its outer core. This magnetic field protects our planet from harmful solar radiation and cosmic rays. However, other bodies in the solar system exhibit different magnetic properties. Jupiter has the strongest magnetic field of any planet in the solar system, which is created by its rapid rotation and the motion of metallic hydrogen within its interior. This powerful magnetic field traps charged particles in a vast radiation belt, creating extreme conditions for any spacecraft exploring the region. The intense radiation environment poses a significant challenge for missions to Jupiter and its moons. In contrast, Mars has a weak and patchy magnetic field, suggesting that its interior has cooled significantly and its dynamo activity has ceased. This loss of magnetic protection has likely contributed to the loss of the Martian atmosphere over billions of years, raising questions about the planet's past habitability. Another magnetic mystery lies with Mercury, which has a surprisingly strong magnetic field despite its small size and slow rotation. This anomaly raises questions about the dynamics of its core and the processes that generated its magnetic field. Understanding Mercury's magnetic field could provide insights into the formation and evolution of terrestrial planets. The solar system is also home to various enigmatic phenomena related to its structure and dynamics. For example, the discovery of Planet 9, a hypothetical massive planet lurking beyond Pluto, has sparked considerable debate among astronomers. Observations of unusual orbits of distant trans-Neptunian objects suggest the gravitational influence of a yet-to-be-discovered planet. While evidence for Planet 9 remains circumstantial, its potential existence has implications for our understanding of the solar system's architecture and the processes that shaped it. Additionally, the phenomenon of rogue planets, planets that wander through the galaxy without a parent star, poses questions about planetary formation and dynamics. These free-floating worlds may originate from ejected planets in young star systems or form independently in dark molecular clouds. The study of rogue planets could reveal insights into the diversity of planetary systems and the potential for life in the universe. The solar system is also filled with debris from its formation, including asteroids, comets, and meteoroids. The study of these objects offers valuable information about the building blocks of planets and the processes that shaped our solar system. Some asteroids, like Bennu and Ryugu, are considered time capsules from the early solar system, preserving ancient material that can provide insights into the conditions present during planet formation. NASA's OSIRIS-RX mission successfully collected samples from the asteroid Bennu and is set to return these samples to Earth in 2023. Similarly, Japan's Hayabusa 2 mission collected samples from the asteroid Ryugu and returned them to Earth in late 2020. Analyzing these samples could provide valuable insights into the origins of our solar system and the materials that contributed to the formation of Earth and other planets. Moreover, the study of comets reveals intriguing information about the early solar system. Comets are composed primarily of ice, dust, and rocky material, and they are often referred to as dirty snowballs. When comets approach the sun, the heat causes the ices to sublimate, creating spectacular tails that can stretch for millions of kilometers. The study of comets can shed light on the early conditions of the solar system and the processes that led to the formation of planets. One notable comet is Comet 67P/Churyumov-Gerasimenko, which was the target of the European Space Agency's Rosetta mission. The spacecraft orbited the comet and deployed the Philae lander to its surface in 2014. Rosetta's findings revealed that 67P is a complex object with a varied surface, containing both active and inactive regions. The mission provided valuable insights into the composition of comets and their role in delivering water and organic molecules to the early Earth. As we peer deeper into the solar system, we continue to uncover mysteries that challenge our understanding of the universe. Each new discovery raises further questions and expands our knowledge of the cosmos. The advancements in technology, including powerful telescopes and sophisticated space missions, allow us to explore previously uncharted territories and unlock the secrets of our solar system. The ongoing exploration of the solar system is not just a quest for knowledge, it also reflects humanity's innate curiosity and desire to understand our place in the universe. Each mission, each discovery, brings us closer to unraveling the mysteries of our celestial neighborhood and the broader cosmos beyond. As we move forward, the future of solar system exploration looks promising. With missions planned to return samples from Mars, explore the icy moons of Jupiter and Saturn, and investigate the far reaches of the Kuiper Belt, we stand on the brink of new discoveries that could reshape our understanding of the solar system. The pursuit of knowledge about our celestial neighborhood continues to inspire scientists and enthusiasts alike, igniting a sense of wonder and curiosity about the mysteries that lie beyond our planet. Ultimately, the solar system is a dynamic and complex environment, rich with stories waiting to be told. Each celestial body, from the innermost planets to the distant reaches of the Oort cloud, has its own unique history and secrets. By continuing to explore and study our solar system, we can hope to answer fundamental questions about the nature of life, the origins of our planet, and the cosmic forces that shape the universe. The mysteries of the solar system are far from solved, and as we look to the stars, we embark on a journey that promises to reveal the wonders of our celestial home. As we venture deeper into the exploration of our solar system, it is essential to consider the dynamics and interactions between the various celestial bodies. The gravitational dance between planets, moons, asteroids, and comets shapes the architecture of our solar system and influences the conditions for potential life. Understanding these interactions not only enhances our knowledge of individual bodies, but also provides insights into the history and evolution of the entire system. One fascinating aspect of these dynamics is the concept of orbital resonances. Orbital resonance occurs when two orbiting bodies exert regular, periodic gravitational influences on each other, often because their orbital periods are related by a ratio of small integers. A classic example within our solar system is the orbital resonance between Jupiter and the asteroid belt, particularly the Kirkwood gaps, regions of the belt where few asteroids are found. These gaps are the result of gravitational perturbations from Jupiter, which clear out certain orbits, leading to the absence of asteroids in those regions. Understanding these resonances is crucial as they can lead to the stability or instability of orbits, influencing the likelihood of collisions and the distribution of objects within the solar system. The study of the Kuiper Belt, a region beyond Neptune populated with icy bodies and dwarf planets like Pluto, provides another intriguing case of gravitational interactions. The Kuiper Belt objects, KBOs, exhibit a variety of orbits, some of which are influenced by the gravitational pull of Neptune. These interactions can cause KBOs to migrate inward toward the inner solar system or, conversely, to be ejected into more distant orbits. The exploration of the Kuiper Belt not only sheds light on the formation of our solar system but also poses questions about the potential for additional undiscovered planets or massive objects within this region. The importance of the solar wind, a stream of charged particles released from the sun, also cannot be overstated. This solar wind interacts with planetary magnetic fields, shaping the environments of planets and moons throughout the solar system. For instance, Earth's magnetic field protects us from the solar wind's effects, but Mars, with its weak magnetic field, is much more vulnerable. This vulnerability has significant implications for Mars' atmosphere and potential habitability. As the solar wind strips away the Martian atmosphere, it contributes to the planet's current barren and inhospitable state. The study of solar wind interactions helps us understand the climatic and atmospheric evolution of other planets and moons. Comets, with their highly elliptical orbits, are another compelling area of study in understanding the solar system's dynamics. Originating from the Kuiper Belt or the Oort cloud, comets travel from the far reaches of the solar system towards the sun, often exhibiting spectacular tails as their ices vaporize. These comets can also be influenced by the gravitational pull of planets, altering their trajectories and sometimes leading to potential impacts with Earth or other bodies. The exploration of comets, such as Comet Hale-Bopp and Comet Neowise, provides insight into the primordial materials that existed in the early solar system and the processes that shaped our planetary neighborhood. Furthermore, the role of impact events has played a crucial part in the solar system's history. The surfaces of many celestial bodies bear the scars of impacts, from the Moon's heavily cratered surface to the giant impact basins on Mercury and Mars. These impacts have not only shaped the surfaces of these bodies, but have also influenced their geological and atmospheric evolution. The study of impact cratering offers valuable clues about the history of our solar system, including insights into the frequency and size of past impacts. The Moon serves as a critical case study for understanding the impact history of the solar system. The large number of craters visible on the lunar surface provides a record of the various bodies that collided with it over billions of years. The age and distribution of these craters allow scientists to estimate the timing and intensity of bombardment events, contributing to our understanding of the solar system's formative years. The Moon's geological history is intricately linked to the processes that shaped not only its surface but also the Earth, as the two bodies have influenced each other over time. As we explore the solar system, the search for extraterrestrial life remains a central theme in our investigations. While Mars and the icy moons of Jupiter and Saturn have garnered significant attention due to their potential habitability, the concept of life existing in extreme environments expands our search to even the most inhospitable locations. Hydrothermal vents on the ocean floor of Earth demonstrate that life can thrive in complete darkness and extreme pressure, challenging our preconceived notions about where life can exist. The exploration of extremophiles, organisms that can survive in extreme conditions, on Earth has profound implications for astrobiology. For example, certain microorganisms can survive in environments with high radiation levels, extreme temperatures, or high salinity. This resilience suggests that similar forms of life could potentially exist in harsh environments elsewhere in the solar system, such as the subsurface oceans of icy moons or the atmospheres of gas giants. The study of astrobiology is a rapidly evolving field that examines the potential for life beyond Earth. This interdisciplinary science combines knowledge from biology, chemistry, geology, and astronomy to investigate the conditions necessary for life and the potential for its existence on other planets and moons. By understanding the fundamental principles of life on Earth, scientists can develop models and hypotheses to guide the search for life in the cosmos. In recent years, the discovery of exoplanets, planets outside our solar system, has transformed our understanding of planetary systems and the potential for life elsewhere in the universe. Thousands of exoplanets have been identified, with a growing number found in the habitable zone where conditions may be right for liquid water to exist. The techniques used to discover and characterize these exoplanets also inform our understanding of planetary formation and evolution, shedding light on the processes that may be at play in our own solar system. Returning to our solar system, the ongoing search for life extends to the outer planets and their moons, with missions planned to further investigate these intriguing environments. The James Webb Space Telescope, launched in late 2021, is poised to revolutionize our understanding of the universe, providing unprecedented insights into the atmospheres of exoplanets and the potential signatures of life. As we continue to explore the solar system, each new mission and discovery adds to the mosaic of knowledge that helps us piece together the history of our cosmic neighborhood. Additionally, the potential for resource utilization beyond Earth has become a significant area of interest. As humanity looks to the stars, the idea of utilizing resources from other celestial bodies, such as asteroids and the moon, is gaining traction. These resources could provide raw materials for construction, fuel for space travel, and even essential elements for sustaining human life in future missions to Mars or beyond. The study of asteroid composition and the feasibility of mining them for valuable resources could redefine our approach to space exploration and the sustainability of human presence in space. As we delve deeper into the mysteries of our solar system, we are reminded of the interconnectedness of all celestial bodies and the dynamic forces at play. Each discovery leads to new questions and avenues for exploration, driving our curiosity and desire to understand the universe. The journey through the solar system is not merely a scientific endeavor, it embodies humanity's quest for knowledge, pushing the boundaries of our understanding and expanding our horizons. Ultimately, the solar system is a vast and intricate tapestry woven with the threads of time, space, and the forces that govern the cosmos. As we continue to explore its mysteries, we are not just uncovering the secrets of our immediate surroundings. We are also grappling with profound questions about our place in the universe and the nature of existence itself. The solar system, with its diverse range of planets, moons, and phenomena, offers a rich landscape for exploration and discovery, inviting us to venture further into the unknown. As we look ahead to the future, the ongoing exploration of our solar system holds great promise. With missions to Mars, the icy moons of the outer planets, and the distant reaches of the Kuiper Belt, we are poised to unlock further secrets of our cosmic home. The synergy of scientific inquiry, technological innovation, and human curiosity drives our quest for knowledge, and each step we take brings us closer to understanding the mysteries that lie beyond our world. The solar system remains a captivating realm of exploration, filled with mysteries waiting to be unraveled. From the potential for life on Mars to the enigmatic moons of Jupiter and Saturn, the ongoing investigations into our celestial neighborhood challenge us to rethink our understanding of life, planetary dynamics, and the very fabric of the cosmos. As we continue our journey through the solar system, we are reminded that the pursuit of knowledge is an endless endeavor, one that inspires us to reach for the stars and embrace the mysteries that lie beyond. Our exploration of the solar system is a testament to human curiosity, ingenuity, and the unyielding desire to seek out the unknown. As we unlock the secrets of the solar system, we not only expand our knowledge but also enrich our understanding of the universe and our place within it. As we delve deeper into the solar system, it becomes evident that each planet and moon holds unique characteristics that contribute to our overall understanding of the universe. The exploration of these celestial bodies not only reveals their histories but also allows us to draw connections to Earth's past and the broader cosmic narrative. Take, for instance, Venus, often referred to as Earth's sister planet due to its similar size and composition. However, its current state starkly contrasts with that of our home planet. Venus has a thick, toxic atmosphere composed mainly of carbon dioxide, with clouds of sulfuric acid, leading to an extreme greenhouse effect that traps heat. Surface temperatures on Venus can soar above 900 degrees Fahrenheit, 475 degrees Celsius, making it the hottest planet in the solar system. Understanding the atmospheric dynamics of Venus provides vital insights into climate change and planetary evolution, highlighting how different environmental conditions can lead to drastically different planetary outcomes. The study of Venus also raises questions about the planet's volcanic activity. Evidence suggests that Venus may still be geologically active, with numerous volcanoes and lava flows observed on its surface. The absence of significant erosion features hints at a relatively young surface age, indicating that volcanic activity may have shaped the landscape in more recent geological times. Investigating the volcanic history of Venus not only sheds light on its geology but also invites comparisons to Earth's volcanic processes, enhancing our understanding of planetary dynamics. In contrast, the gas giants, Jupiter and Saturn, offer a fascinating glimpse into the formation of the solar system. Jupiter, the largest planet in our solar system, is a swirling mass of gas and storms, with a prominent feature known as the Great Red Spot, a massive storm that has been raging for centuries. The study of Jupiter's atmosphere and magnetic field reveals critical information about the planet's internal structure and evolution. The Juno mission, launched in 2011, has provided unprecedented data about Jupiter's gravitational and magnetic fields, shedding light on its formation and the processes that govern its behavior. Saturn, renowned for its stunning rings, presents its own set of mysteries. The rings of Saturn are composed of countless particles ranging in size from tiny ice grains to massive boulders. The origin of these rings remains a topic of active research. Some theories propose that they may be remnants of a destroyed moon or material that never coalesced into a moon. Investigating the dynamics of Saturn's rings and their interaction with the planet's moons can provide insights into the processes of planetary formation and the stability of celestial bodies. The moons of the gas giants are equally compelling. Europa, one of Jupiter's largest moons, is a prime candidate in the search for extraterrestrial life. Beneath its icy crust lies a vast subsurface ocean, potentially containing more than twice the amount of water found on Earth. The discovery of plumes erupting from Europa's surface suggests that this ocean may be interacting with the moon's rocky mantle, creating conditions that could support microbial life. Future missions, such as NASA's Europa Clipper, aim to further investigate this intriguing moon and assess its habitability. Similarly, Saturn's moon Enceladus has garnered attention for its geysers that eject water vapor and organic compounds into space. These plumes, which emanate from a subsurface ocean, provide direct evidence of the moon's potential for habitability. Analyzing the composition of these plumes can yield critical information about the ocean below and the conditions that may support life. The Cassini mission, which studied Saturn and its moons, has significantly advanced our understanding of Enceladus, opening new avenues for exploration and research. Titan, Saturn's largest moon, presents a unique environment unlike any other in the solar system. With its dense atmosphere and lakes of liquid methane and ethane, Titan is the only known moon with a substantial atmosphere and stable bodies of surface liquid. The study of Titan's atmosphere and its complex organic chemistry offers valuable insights into prebiotic conditions and the potential for life in environments vastly different from those on Earth. The upcoming Dragonfly mission aims to explore Titan's diverse landscapes and investigate its potential habitability by flying to various locations on its surface. In addition to these fascinating moons, the outer solar system also includes a variety of smaller bodies, such as comets and asteroids, which provide crucial information about the solar system's formation. Comets, often referred to as dirty snowballs, consist of ice, dust, and rocky material. Their orbits bring them close to the Sun, where they develop tails as their icy components vaporize. The study of comets, such as Comet 67P/Churyumov-Gerasimenko, has revealed insights into the primordial materials that formed the solar system. The Rosetta mission, which orbited and landed on this comet, provided data that may shed light on the conditions of the early solar system and the building blocks of life. Asteroids, too, are remnants from the solar system's formation, with the asteroid belt between Mars and Jupiter serving as a treasure trove of information. These rocky bodies vary widely in size and composition, with some containing valuable metals and materials. The exploration of asteroids, such as the asteroid Bennu by NASA's OSIRIS-RX mission, is aimed at returning samples to Earth for analysis. Studying these samples can provide insights into the early solar system, the processes that shaped the planets, and even the origins of organic materials necessary for life. Furthermore, the concept of planetary protection has gained increasing attention as our exploration of the solar system expands. As we send spacecraft to investigate other worlds, it is crucial to prevent contamination by terrestrial microbes. This is particularly important when exploring potentially habitable environments like Mars or the icy moons of Jupiter and Saturn. The protection of these celestial bodies not only preserves their natural state, but also ensures the integrity of our scientific investigations. International guidelines and protocols have been established to minimize the risk of contamination and safeguard our search for extraterrestrial life. As we reflect on the mysteries of the solar system, it becomes clear that the exploration of these celestial bodies is not merely an academic pursuit. It is a quest that ignites our imagination and inspires future generations. The sense of wonder and curiosity that drives humanity to reach for the stars is rooted in our desire to understand the cosmos and our place within it. Each new discovery brings us closer to unraveling the mysteries of our solar neighborhood and invites us to ponder the profound questions of existence. The solar system, with its diverse array of planets, moons, asteroids, and comets, serves as a natural laboratory for studying the fundamental processes that govern planetary formation and evolution. By investigating the unique characteristics of these celestial bodies, we gain insights into the conditions necessary for life and the history of our own planet. The pursuit of knowledge is a testament to human ingenuity and resilience, driving us to confront challenges and embrace the unknown. Looking to the future, the ongoing exploration of the solar system promises to unveil new mysteries and deepen our understanding of the universe. The collaboration between space agencies, scientists, and researchers around the world fosters innovation and propels our quest for discovery. As we stand at the forefront of a new era in space exploration, the potential for groundbreaking discoveries is limitless. The solar system remains a captivating realm of exploration, rich with mysteries waiting to be unraveled. From the potential for life on Mars to the stunning diversity of moons and the enigmatic nature of asteroids and comets, our understanding of the solar system is constantly evolving. The journey through the solar system embodies humanity's quest for knowledge, pushing the boundaries of our understanding and expanding our horizons. As we continue to explore its mysteries, we are reminded that the pursuit of knowledge is an endless endeavor, one that inspires us to reach for the stars and embrace the mysteries that lie beyond. Ultimately, our exploration of the solar system is a testament to the human spirit, a spirit that seeks to understand, to innovate, and to connect with the universe. Each discovery adds a new chapter to the story of our cosmic journey, reminding us that we are not merely observers but active participants in the unfolding narrative of existence. As we continue to probe the depths of space and unlock the secrets of the solar system, we embark on a journey that transcends time and space, one that reaffirms our shared humanity and our collective aspiration to explore the great unknown. As we continue our exploration of the solar system, we must not overlook the significance of the Sun itself, the central star around which all planets orbit. The Sun is more than just a source of light and warmth. It is a complex and dynamic entity that plays a crucial role in shaping the solar system and influencing the environments of the planets within it. Understanding the Sun's structure, behavior, and impact on the solar system can provide valuable insights into the broader workings of stars and the evolution of planetary systems throughout the universe. At its core, the Sun is composed of hydrogen and helium undergoing nuclear fusion to produce energy. This process generates immense heat and light, creating the conditions necessary for life on Earth. The Sun's energy fuels weather patterns, ocean currents, and photosynthesis, supporting the intricate web of life that thrives on our planet. However, the Sun is also a source of cosmic phenomena that can have profound effects on the solar system. One of the most fascinating aspects of the Sun is its magnetic field, which generates solar activity such as sunspots, solar flares, and coronal mass ejections, CMEs. Sunspots are dark patches on the Sun's surface caused by magnetic activity that disrupts the flow of heat. These areas are cooler than their surroundings and often appear in cycles, with an approximately 11-year solar cycle influencing their frequency and intensity. Understanding these cycles is essential, as they can affect space weather, which in turn impacts satellite operations, communications, and even power grids on Earth. Solar flares are sudden and intense bursts of radiation resulting from the release of magnetic energy stored in the Sun's atmosphere. These explosive events can emit high-energy particles and radiation across the electromagnetic spectrum, including X-rays and radio waves. When directed toward Earth, solar flares can disrupt communication systems, damage satellites, and even pose risks to astronauts in space. Monitoring solar activity is crucial for understanding these phenomena and mitigating their effects on our technological infrastructure. CMEs are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When directed toward Earth, these ejections can interact with our planet's magnetic field, resulting in geomagnetic storms. These storms can produce spectacular auroras, known as the northern and southern lights, as charged particles collide with the Earth's atmosphere. However, they can also induce electrical currents in power lines and pipelines, potentially causing widespread disruptions. Understanding the Sun's behavior and its impact on the solar system requires continuous monitoring and research. Space missions, such as NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter, are dedicated to studying the Sun up close. The Parker Solar Probe, launched in 2018, is designed to approach the Sun closer than any previous spacecraft, gathering data on its atmosphere and magnetic fields. This mission aims to unravel the mysteries of solar wind and solar activity, enhancing our understanding of the Sun's influence on the solar system and beyond. Another intriguing aspect of the solar system lies in the study of dwarf planets, a category that includes objects such as Pluto, Eris, Haumea, and Makemake. Once considered planets, these celestial bodies have been reclassified due to their size and characteristics. Dwarf planets offer unique insights into the composition and dynamics of the outer solar system, challenging our understanding of planetary formation. Pluto, perhaps the most famous dwarf planet, was reclassified in 2006, sparking debates within the scientific community and popular culture. The New Horizons mission, which flew by Pluto in 2015, provided the first close-up images and data about this distant world. The images revealed a diverse and geologically active surface, complete with mountains, plains, and icy features. Pluto's atmosphere, primarily composed of nitrogen, shows signs of complex weather patterns and seasonal changes, hinting at a dynamic environment. Eris, another prominent dwarf planet located in the scattered disk region beyond Neptune, is even more massive than Pluto. Its discovery in 2005 led to the redefinition of the criteria for planetary status. Eris is thought to possess a thin atmosphere that may freeze and sublimate based on its distance from the Sun, demonstrating the variety of conditions that can exist among these distant worlds. Haumea and Mi'kmaq, both found in the Kuiper Belt, further illustrate the diversity of dwarf planets. Haumea is unique due to its elongated shape and rapid rotation, which has led scientists to hypothesize about its formation and collision history. Mi'kmaq, on the other hand, is notable for its reddish coloration, suggesting the presence of organic compounds on its surface. The study of these dwarf planets expands our understanding of the solar system's formation and evolution, highlighting the complexity of celestial bodies that lie beyond the traditional planets. Additionally, the Kuiper Belt and the Oort cloud are two regions that hold many mysteries regarding the solar system's formation and the origins of comets. The Kuiper Belt, located beyond the orbit of Neptune, is populated by numerous icy bodies, including dwarf planets and comets. This region is thought to contain remnants from the early solar system, providing clues about its formation and the conditions present during that time. Comets that originate from the Kuiper Belt, such as Comet Hale-Bopp and Comet Neowise, offer spectacular displays as they approach the Sun, revealing the composition of their icy nuclei. The Oort cloud, a hypothetical region thought to lie much farther from the Sun, is believed to contain a vast reservoir of comets. Unlike the Kuiper Belt, which is relatively flat and disk-like, the Oort cloud is thought to be spherical and may extend halfway to the nearest stars. The origins and dynamics of this distant cloud remain a topic of research and speculation, as no direct observations of the Oort cloud have yet been made. However, studying long-period comets that originate from this region can provide valuable insights into the early solar system and the processes that govern its evolution. As we reflect on the mysteries of the solar system, we must also acknowledge the role of human exploration and the technological advancements that have made our discoveries possible. The development of spacecraft, telescopes, and advanced scientific instruments has revolutionized our understanding of the universe. Space missions, whether crewed or uncrewed, have pushed the boundaries of exploration, providing us with unparalleled insights into the cosmos. The International Space Station, ISS, serves as a testament to human collaboration in space exploration. This orbiting laboratory has been home to astronauts from various nations, conducting experiments that advance our understanding of biology, physics, and materials science and microgravity. The ISS has also served as a platform for testing technologies that will be essential for future deep space missions, including those to Mars and beyond. In the realm of robotic exploration, missions like the Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance have dramatically transformed our knowledge of the Red Planet. These rovers have traversed the Martian surface, conducting experiments, analyzing soil and rock samples, and searching for signs of past life. Perseverance, launched in 2020, is equipped with advanced scientific instruments designed to seek out signs of ancient microbial life and collect samples for potential return to Earth in future missions. The desire to explore other planets has also driven missions to the outer solar system. The Voyager spacecraft, launched in 1977, have provided humanity with its first detailed views of the gas giants, sending back invaluable data about their atmospheres, moons, and magnetic fields. Voyager 1 and Voyager 2 have continued their journey into interstellar space, providing data about the heliosphere and the environment beyond our solar system. The prospect of human exploration beyond Earth is increasingly within our reach. Space agencies and private companies are actively working on missions to send humans to Mars and establish a sustainable presence on the Moon. These endeavors not only aim to expand our knowledge of other worlds, but also to inspire future generations to pursue careers in science, technology, engineering, and mathematics, STEM. The goal of establishing a human presence on Mars is particularly ambitious, requiring advancements in life support systems, propulsion technologies, and habitat construction. The mysteries of the solar system serve as both a source of inspiration and a reminder of our place in the cosmos. Each discovery and mission reinforces our connection to the universe and prompts us to ponder fundamental questions about our existence. As we continue to explore and study the solar system, we are challenged to consider our responsibilities as stewards of our home planet and as explorers of the wider universe. The solar system is a vast and dynamic realm, rich with mysteries that continue to captivate our imagination. From the intricate dynamics of the sun to the diverse characteristics of the planets and their moons, each celestial body offers a unique perspective on the history and evolution of our solar neighborhood. The ongoing exploration of the solar system is a testament to human curiosity and ingenuity, driving us to uncover the secrets of the universe and expand our understanding of the cosmos. As we venture further into space, we are reminded that the journey of discovery is not merely about reaching distant worlds, it is about deepening our connection to the universe and our understanding of ourselves. The quest for knowledge is a never-ending endeavor, and as we continue to push the boundaries of exploration, we embrace the mysteries that lie ahead, forging a path toward a brighter future for humanity and the world we call home. As we delve deeper into the mysteries of the solar system, it is essential to explore the diverse range of celestial phenomena that shape our understanding of planetary bodies and their environments. The solar system is a dynamic landscape, characterized by its ever-changing atmospheres, surface features, and geological activity. Each planet and moon presents a unique set of challenges and opportunities for scientific inquiry, revealing the complexity of planetary science. One of the most striking features of our solar system is the vast variety of planetary atmospheres. For instance, Venus, often referred to as Earth's sister planet, possesses an atmosphere primarily composed of carbon dioxide, with clouds of sulfuric acid. This thick, toxic atmosphere creates an extreme greenhouse effect, resulting in surface temperatures hot enough to melt lead, around 900 degrees Fahrenheit, 475 degrees Celsius. The atmospheric pressure on Venus is also about 92 times that of Earth, equivalent to the pressure experienced at a depth of nearly a mile, 1.5 kilometers, underwater. These harsh conditions make Venus a challenging target for exploration, yet they offer valuable insights into atmospheric science and climate dynamics. On the other hand, Mars has garnered significant attention due to its more Earth-like features and the potential for past life. The Martian atmosphere is thin and composed mostly of carbon dioxide, with only trace amounts of oxygen. This thin atmosphere, combined with low temperatures and high radiation levels, presents significant challenges for any future human missions. However, Mars is home to some of the solar system's most remarkable geological features, including the largest volcano, Olympus Mons, and the deepest canyon, Valles Marineris. These formations suggest a history of volcanic and tectonic activity, raising questions about the planet's past and its potential habitability. The exploration of Mars has been propelled by various robotic missions, including the Mars Reconnaissance Orbiter, which has provided high-resolution images of the Martian surface and revealed evidence of water in the form of ice, seasonal dark streaks, and ancient riverbeds. The Curiosity and Perseverance rovers are equipped with sophisticated scientific instruments that analyze soil and rock samples, searching for signs of past microbial life and studying the planet's geology. Perseverance, in particular, aims to collect samples for a future return mission to Earth, potentially bringing back critical evidence of Mars' past. Jupiter, the largest planet in our solar system, presents another set of mysteries. Its atmosphere is composed mainly of hydrogen and helium, with striking bands of clouds that result from powerful jet streams. Jupiter is famous for the Great Red Spot, a massive storm larger than Earth that has persisted for centuries. The study of Jupiter's atmosphere can provide insights into the dynamics of gas giants, including weather patterns, cloud formation, and the processes that drive such colossal storms. Jupiter's moons are equally fascinating. Europa, one of its most intriguing moons, is covered in a thick layer of ice, beneath which lies a subsurface ocean. The potential for a liquid ocean, coupled with the presence of essential chemical elements, raises the possibility of life existing beyond Earth. The upcoming Europa Clipper mission, set to launch in the 2020s, aims to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, further investigating its habitability. Another of Jupiter's moons, Ganymede, is the largest moon in the solar system and the only moon known to possess its magnetic field. Ganymede's surface features a combination of two types of terrain: dark regions filled with impact craters and lighter regions characterized by grooves and ridges. The combination of these features suggests a complex geological history that may involve tectonic processes and potentially a subsurface ocean, similar to Europa. Saturn, known for its stunning rings, is another giant planet that captures the imagination. Its atmosphere is primarily composed of hydrogen and helium, similar to Jupiter, but it also features a variety of storms and cloud patterns. Saturn's rings are composed of countless small particles, ranging in size from tiny grains to large chunks of ice and rock. The exact origin of these rings remains a topic of research, with hypotheses suggesting they may have formed from the debris of a shattered moon or remnants from the early solar system. Saturn's moons, particularly Titan and Enceladus, have become focal points of exploration. Titan, the second largest moon in the solar system, possesses a thick atmosphere rich in nitrogen and methane. The presence of lakes and rivers of liquid methane on its surface presents a unique environment that is unlike any other celestial body in the solar system. Titan's complex chemistry and potential for prebiotic conditions make it a prime target for future exploration, with missions such as the Dragonfly lander planned for the 2030s to investigate its surface and atmosphere. Enceladus, on the other hand, has garnered attention due to its active geysers that erupt from its southern polar region, releasing plumes of water vapor and ice particles into space. These geysers indicate the presence of a subsurface ocean, which raises intriguing possibilities about the moon's habitability. The Cassini spacecraft's close encounters with Enceladus have provided critical data about the composition of its plumes, revealing organic molecules and suggesting that the conditions may be suitable for microbial life. Uranus and Neptune, the ice giants of the solar system, also present a unique set of challenges and mysteries. Uranus is known for its unusual axial tilt, which causes extreme seasonal variations in its atmosphere. Its atmosphere is composed mainly of hydrogen and helium, with traces of methane giving it a bluish hue. Neptune, slightly smaller than Uranus, possesses the strongest winds in the solar system, with speeds reaching over 1,200 miles per hour, 2,000 kilometers per hour. The study of these distant planets can provide insights into the formation and evolution of gas giants, as well as the dynamics of their atmospheres. The exploration of the solar system is not limited to the planets alone. Asteroids and comets also hold valuable clues about the early solar system and the formation of planetary bodies. The asteroid belt, located between Mars and Jupiter, is home to numerous rocky bodies, some of which are remnants from the solar system's formation. Studying these asteroids can provide insights into the processes that led to the formation of terrestrial planets and the evolution of our solar neighborhood. Comets, often referred to as dirty snowballs, are icy bodies that originate from the Kuiper Belt and Oort cloud. When they approach the sun, the heat causes their ices to vaporize, creating a glowing coma and sometimes a tail that stretches for millions of miles. The study of comets can reveal information about the primordial materials that contributed to the formation of planets. Missions like the Rosetta spacecraft, which successfully landed on the comet 67P/Churyumov-Gerasimenko, have provided unprecedented insights into the composition and behavior of these ancient bodies. As we continue to explore the solar system, it is crucial to consider the implications of our discoveries for humanity and our understanding of life's potential beyond Earth. The search for extraterrestrial life has been a driving force behind many space missions, with the underlying question of whether we are alone in the universe. The discovery of subsurface oceans on moons like Europa and Enceladus, the presence of organic molecules on Titan, and the varied conditions found across the solar system raise tantalizing possibilities. Astrobiology, the study of life in the universe, seeks to understand the conditions necessary for life to exist and the potential for life beyond Earth. The exploration of extreme environments on Earth, such as hydrothermal vents and acidic lakes, has provided insights into the adaptability of life and the potential for similar organisms to thrive in harsh extraterrestrial environments. These findings underscore the importance of continued exploration and the development of technologies that can detect biosignatures, indicators of past or present life, on other planets and moons. The solar system is a treasure trove of mysteries waiting to be unraveled. From the dynamic atmospheres of the gas giants to the icy worlds of the Kuiper Belt and the potential habitability of moons like Europa and Titan, each celestial body presents unique challenges and opportunities for scientific inquiry. The ongoing exploration of the solar system not only enhances our understanding of planetary science, but also ignites our curiosity about the nature of life and our place in the universe. As we push the boundaries of exploration and technology, we stand on the brink of discoveries that may reshape our understanding of the cosmos and our role within it. The quest for knowledge is a collective endeavor, and as we gaze at the stars and the mysteries of the solar system, we are reminded of the boundless possibilities that lie ahead, waiting to be discovered. As we delve deeper into the solar system's mysteries, it is essential to examine how these celestial bodies interact with one another and how these interactions have shaped the solar system's history. The dynamics of the solar system are not merely a collection of isolated bodies, they are a complex web of gravitational forces, collisions, and interactions that have significant implications for the evolution of each planet and moon. One of the key factors influencing the structure of the solar system is the gravitational influence of the Sun, which holds over 99% of the solar system's total mass. This immense gravitational pull governs the orbits of all celestial bodies, ensuring that planets, moons, and smaller objects maintain their trajectories within a relatively stable framework. However, the gravitational interactions between these bodies can lead to perturbations in their orbits and even result in collisions. Such events have played a crucial role in the history of the solar system. The early solar system was a chaotic environment filled with countless small bodies, many of which collided and merged to form the planets we see today. The Late Heavy Bombardment, a period that occurred approximately 4 billion years ago, is believed to have resulted in a spike in impact events that shaped the surfaces of the inner planets. The craters we observe on the Moon, Mercury, and Mars serve as a testament to this turbulent past, providing a geological record of the solar system's formative years. The study of impact craters is crucial for understanding not only the history of individual celestial bodies, but also the broader dynamics of the solar system. For instance, the presence of large impact craters on the Moon's surface provides insights into its geological history, while also indicating the frequency and scale of past impact events. Analyzing the composition of these craters can reveal information about the materials that formed the impacted bodies, as well as the conditions present in the early solar system. In addition to cratering, gravitational interactions between celestial bodies can lead to phenomena such as orbital resonance, which occurs when two orbiting bodies exert regular, periodic gravitational influence on each other. This phenomenon can lead to stability in certain orbits and can also result in chaotic behavior in others. A prime example of this is the relationship between the four largest moons of Jupiter, known as the Galilean moons, Io, Europa, Ganymede, and Callisto. These moons are in a gravitational resonance known as the Laplace resonance, where their orbital periods are related in such a way that their gravitational interactions lead to a stable configuration. This resonance plays a crucial role in maintaining the geological activity observed on Io and Europa, as the tidal forces generated by their gravitational interactions lead to heating of their interiors. The role of tidal forces extends beyond the Galilean moons and can be observed on other celestial bodies as well. For instance, Saturn's moon Enceladus experiences significant tidal heating due to its gravitational interactions with Saturn and neighboring moons. This heating contributes to the geological activity that drives the geysers observed on its surface, further supporting the hypothesis of a subsurface ocean. The dynamics of tidal forces illustrate how interactions between celestial bodies can influence geological processes, potentially creating habitable environments in otherwise inhospitable settings. Moreover, the solar system is not static. It continues to evolve over time due to ongoing processes such as planetary migration. This phenomenon occurs when a planet's gravitational influence affects the distribution of material in the protoplanetary disk from which it formed, leading to shifts in its orbit. The migration of gas giants, particularly Jupiter and Saturn, is believed to have played a significant role in shaping the current architecture of the solar system. For example, the NICE model suggests that the outward migration of these gas giants may have led to the scattering of small bodies in the outer solar system, resulting in the formation of the Kuiper Belt and the dynamics observed among trans-Neptunian objects. The study of the Kuiper Belt, home to numerous icy bodies, including dwarf planets like Pluto and Eris, has unveiled fascinating insights into the early solar system. The Kuiper Belt is a region that extends from the orbit of Neptune to approximately 50 astronomical units, AU, from the Sun. It is believed to contain remnants from the solar system's formation, offering clues about the conditions and processes that prevailed in its infancy. Understanding the composition and behavior of Kuiper Belt objects, KBOs, can shed light on the distribution of material in the early solar system and the potential for future exploration of these distant worlds. Pluto, once considered the ninth planet, is now classified as a dwarf planet, and its status has sparked debates within the astronomical community. The discovery of other KBOs similar in size to Pluto has prompted discussions about the definition of a planet and the diversity of objects within the solar system. Despite its reclassification, Pluto remains an intriguing target for exploration. The New Horizons mission, which conducted a flyby of Pluto in 2015, provided the first detailed images and data about its surface, revealing a complex landscape characterized by mountains, plains, and a dynamic atmosphere. The findings from this mission challenged our understanding of icy bodies in the outer solar system and underscored the importance of continued exploration to refine our knowledge. Beyond the Kuiper Belt lies the Oort cloud, a hypothetical region thought to contain a vast number of icy bodies and comets. While the Oort cloud has not yet been directly observed, its existence is inferred from the behavior of long-period comets that originate from this distant region. The study of comets and their trajectories can provide insights into the conditions of the early solar system, as well as the processes that govern the evolution of celestial bodies over time. As we explore the mysteries of the solar system, it is essential to recognize the technological advancements that have made these discoveries possible. The development of powerful telescopes, robotic spacecraft, and sophisticated instruments has revolutionized our ability to study celestial bodies from a distance. Space missions such as the Hubble Space Telescope, the Mars rovers, and the Voyager spacecraft have provided invaluable data that have expanded our understanding of the solar system and its complexities. The future of solar system exploration is promising, with a number of exciting missions on the horizon. NASA's Artemis program aims to return humans to the moon, paving the way for a sustainable lunar presence and eventual missions to Mars. The exploration of the moon's south pole, where water ice is believed to exist, holds the potential for significant scientific discoveries and the establishment of a base for future deep space exploration. Mars remains a focal point for exploration, with planned missions such as the Mars Sample Return mission, which seeks to bring samples back to Earth for detailed analysis. The understanding gained from studying Martian geology, climate, and potential biosignatures could revolutionize our knowledge of planetary processes and the conditions necessary for life. In addition to these missions, there are plans to explore the outer solar system further. The Europa Clipper mission will conduct detailed investigations of Europa's ice shell and subsurface ocean, seeking to answer critical questions about its habitability. The Dragonfly mission aims to explore Titan's surface and atmosphere, investigating its prebiotic chemistry and the potential for life in its methane lakes. The mysteries of the solar system continue to captivate scientists and the public alike, driving our desire to explore and understand our cosmic neighborhood. As we venture further into the depths of space, we are reminded of our place within the universe and the profound questions that remain unanswered. The exploration of the solar system is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. Each discovery, whether it be the intricate details of a distant planet or the enigmatic behavior of a comet, contributes to our understanding of the cosmos and the forces that shape our world. In summary, the solar system is a dynamic and complex environment filled with mysteries waiting to be uncovered. From the diverse atmospheres of the inner planets to the icy realms of the outer solar system, each celestial body presents unique challenges and opportunities for scientific inquiry. The interactions between these bodies, influenced by gravitational forces, impact their geological activity and contribute to the evolution of the solar system. As we continue to explore, we not only enhance our understanding of planetary science, but also open doors to new possibilities for the existence of life beyond Earth. The journey of exploration is far from over, and as we gaze at the stars and the wonders of our solar system, we are reminded that there is still much to learn, discover, and understand about the universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.